This talk explores the physics of intelligence, specifically focusing on the Fermionic Mind hypothesis, a physics-based consciousness framework. This domain has traditionally been the purview of philosophy and religion, but in the 20th century, consciousness increasingly became a subject of scientific inquiry. Today, various hypotheses about consciousness exist in the literature. Still, none fully address the hard problem of consciousness, the how, what, and why of our conscious experience. The hard problem of consciousness refers to the philosophical question of why and how physical processes in the brain give rise to subjective experiences. Consciousness constantly reformulates itself in pursuit of a balanced state. This self-regulation introduces a degree of unpredictability and independence from the environment, contributing to the profound mystery surrounding the how of consciousness. The question, what does it feel like to be conscious, explores the origins of subjective experience and awareness. For example, personal experiences differ significantly from the sensory inputs and neural activations that represent those inputs. The Fermionic Mind hypothesis addresses this contradiction by integrating entropy and energy dynamics into traditional neuroscientific research. Our approach not only reconciles this contradiction, but also suggests that the rich and complex sensory world referred to as the what of consciousness arises from the thermodynamic regulation of the neural system. Consciousness, as we understand it, is inseparable from the physical body. This concept, known as embodiment, emphasizes how the nature of the physical body tailors our mental states. This focus on embodiment has profound implications for the notion of machine consciousness. Furthermore, intellect requires the intuition of the physical environment, necessitating the incorporation of physical laws into a particle-like organization. When examining the thermodynamic processes of cognition, we note that thermodynamic cycles are reversible. The fundamental thermodynamic cycle is a Carnot cycle. The reverse Carnot cycle is an endothermic process, meaning it absorbs and accumulates energy, whereas the Carnot cycle dissipates energy. The cycles represent the direction of mental energy, often referred to as psychological spin. At the top right, an upspin signifies the endothermic cycle, whereas a downspin at the bottom demonstrates a loss of cognitive complexity. Fermions, which are particles that obey the Pauli exclusion principle, possess half spin and exhibit spinor behavior. In spinors, one complete rotation of the wave function turns it into its negative. This contrasts a classical object which returns to its original state after a full rotation. For fermions, two complete turns are required to return to the original wave function. The adoption of a fermionic organization by consciousness leads to the psychological spinor the ability to generate opposite emotions or spins to the same experience. For instance, an abuse victim may respond with resentment to a gentle caress from their abuser. This reversal of the attitude is the hallmark of Spiner. The table highlights consciousness as a fermionic organization. The first line is the unity requirement. Similar to fermions, consciousness is also defined by oneness and indivisibility. Fermions interact through 4 fundamental forces, while the elementary forces of motivation are emotions. In the realm of fermions, 2 fundamental forces are particularly prominent in daily life: gravity and electromagnetic force. These are the emotions I will examine more closely. In the case of gravity, mental gravity manifests as stress. Stress can be viewed as a sense of time shortage that leads to impulsivity. Conversely, emotional electromagnetism can be understood as bias, as previously discussed. When exploring the concept of gravity further, we encounter an inverse U-shaped curve representing time perception, shown by a dotted line. Action performance speeds up time perception, culminating in the experience of flow on the top. In contrast, the perception of time increases with both contentment and stress, peaking in states of awe and depression. In moments of awe, our perception of time seems to expand infinitely, while those experiencing depression feel as though time is at a standstill. Nevertheless, the desire for change, represented by a solid line, exhibits a positive slope, increasing linearly with stress. However, the capacity for change shows the opposite trend, characterized by a negative slope. The upside-down U-shaped curve of time perception resembles the Yerkes-Dodson law in psychology. This law expresses the relationship between performance and arousal. It states that optimal performance occurs at a medium level of arousal. This midpoint corresponds to the flow experience, during which time perception speeds up. If we invert this time perception curve, we see that time perception grows with both stress and contentment. We can identify this curve as the derivative of the inverse sine function. From the curve, we can deduce the S-shaped curve of the inverse sine function. On this curve, stress corresponds to a positive field curvature, leading to tightness and constriction, which triggers the impulsivity to escape. On the other hand, the negative field curvature on the right-hand side is an opening up, creating a sense of expansion and a feeling of contentment and a reduced desire for change. Thus, the hard problem of consciousness arises from the energy regulation of cognition and the adoption of the operational principles of the environment, specifically the fermionic organization. We can conclude that consciousness is an organic part of the universe.